Hello, Sioux High Earth Science students. This is Mr. McLeod again. Welcome to part 2 of our Introduction to Astronomy. In this screencast, we will continue our discussion of some astronomy basics, things you will need to know in order for us to get a deeper understanding of our place in our universe and in the cosmos as well. So get your notebooks out and let's roll. First, let's tackle the idea that the light we see from objects in the night sky is ancient, and because of that idea, we are actually looking back in time. Okay, get ready to take some notes. Now take a look at the slide in the screen. It says that light moves at a finite speed. Write that in your notes right now, and then let's try and understand what that means. So pause it and make sure you get that down in your notes. As you probably already know, light moves extremely fast. Write this down if you don't know it already. It moves at 186,000 miles per second, which in metric is 300,000 kilometers per second. So make sure you either know that or get that down in your notes to remind yourself. Now the word finite means that this speed is a limit to how fast light moves, a cosmic speed limit, if you will. This concept was first proposed and explained and proven by Albert Einstein. Even though you probably know that, get it down in your notes right now. Now, using this cosmic speed limit, we can calculate the time it takes for light to reach us from distant objects. For example, it takes 8 minutes for the light from the sun to reach us, and the sun is 93 million miles away. How do we get that? We get that by dividing the 93 million miles by 186,000 miles per second. If you do that in your calculator, you'll get the number 500. That's 500 seconds, which is a little more than 8 minutes. Now, let's take a look then at a star called Sirius. Sirius is a bright star in our sky. And in fact, we'll locate that using a sky chart later in class. We can also use this speed limit in a measurement called the light year. This is the distance light travels in 1 year. So get that definition down in your notes right now, then we'll use it. Okay, so Sirius is a bright star in our sky. In the slide above, it lists its distance as 8 light years away. Now what that means is that the light that left the star is 8 years old when it hits your eye. Are you starting to get the idea that looking at light from these objects in the sky is like looking back in time? So let's look at the Orion Nebula example. How old would that light be once it reaches your eye? Pause this and make a guess in your notes. If you said 1,500 years, you're correct. Now, look at the other 3 examples in this diagram. How old is the light coming from the galaxy 7 billion light years away? If you said that it was 7 billion years old, you're right. Now, how about the galaxy 12 billion light years away? How old is that light? Well, you should be getting the idea now that that light is 12 billion years old when it reaches your eyes. Now, here's a question for you. Look at the third example. Why can't we see any light further out than 14 billion light years? Take a second and think about that, and I'll get back to you with the answer. The answer is you couldn't see it at all. If you said that, congratulations. If not, let's talk about why. If the universe is 13.7 billion years old, then any light older than 13.7 billion years we wouldn't be able to see because it's too old. So we are only able to see light from 13.7 billion light years away and closer. Okay, that finishes up our Part 1 objectives. Now go to Moodle and answer the Part 1 questions, then submit them. When you're done, then move the next slide in this screencast. See you back here in a bit. Okay, let's take a look at what we will learn in our Part 2 objectives. We're going to learn to take a look at our solar system in some kind of scale we can relate to. In other words, we're going to try and get an idea of how huge it is, something that's really tough to do just looking up into the sky. We will also use our understanding of what a light year is to get an idea of how far away the stars are. You probably have a pretty good understanding of that, but we're going to talk about it a little further. Then we'll use a familiar human time scale, namely a calendar, to compare the age of our universe. So let's push on, my budding astronomers. Now let's try and bring our solar system into some kind of a familiar perspective. Let's start with volume and distance. Remember that volume is the amount of space something takes up, where distance is, just like it sounds, the distance between objects from A to B. In the example on the screen, we are using a grapefruit as the size of the sun. So visualize what a grapefruit looks like. Now in your notes, write sun equals size of grapefruit. We will also use that as a starting point for distance. Now in the diagram above, we can make the following observations. So get these in your notes as well. Let's talk about volume first. If we use a grapefruit to represent the size of our sun, then we can all agree that the planets would be smaller than a grapefruit. Now, in our example now, a dust speck represents the smallest former planet, Pluto. And a marble represents our largest planet, Jupiter. Now that means a speck of dust and a marble compared to a grapefruit as the size of our sun. What that means is that all the rest of the planets would be somewhere in between. Get these sizes down in your notes right now, and then we're going to ask some questions. Now, the inner planets are all much smaller than the outer planets. In fact, we call the outer planets gas giants. So in your mind, think of examples of familiar objects that could represent these planets and write them in your notes. Go ahead and do that right now. Okay, now for me, the inner planets might be different size sand grains compared to Pluto, who we just said was a dust speck. While in my mind, the outer planets might be the size of the head of a pin compared to Jupiter. Is that close to what you put? Remember, Jupiter is a huge planet. So head of a pin, a button, somewhere in that kind of time frame would give you a scale of how big those are relative to the sun. Now let's talk about the distance between planets. Again, look at the chart above. Look at the scale on the bottom left of the chart. You'll see a line that represents 100 meters. Now a meter is roughly equal to a yard, So that line equals the length of a football field, about 100 yards. So if we keep the sun the size of a grapefruit and we stay with that scale, we can make a chart that shows the increasing distance from the sun of each of the planets. So let's get this in your notes. Now in this scale, the Earth would be 15 yards from the sun. So if you think about the length of a football field, Earth would be about 15 yards from that grapefruit. Mars would be about 23 yards from the sun or that grapefruit. Not really that far away. Now when we move to some of the outer planets, we see a huge difference. Jupiter would be 76 yards away. Saturn would be 143 yards away. Uranus is 287 yards away, and Neptune would be a whopping 450 yards away from our grapefruit, nearly 5 football fields. So that gives you some idea of the distance between planets. The inner planets relatively close to the sun, the outer planets not so close. Okay, now let's try and get an idea of the dimensions of the galaxy we live in, called the Milky Way. We're going to use the diagram above to make some observations about these dimensions. So get ready to write in your notes again, and you're going to have to, at the end, draw a diagram, so make sure you have some room. Now, locate the central hub of our galaxy on this diagram, and where we are located in relation to that central hub. It says you are here, and there's an X there. Now, in your notes, write that our sun is 26,000 light years away from that central hub. So if you would draw a line from the X where we are located to that central hub, the distance is 26,000 light years. Question for you. What would that mean about the age of the light coming from the center of our galaxy? If you said the light coming from the central hub was 26,000 years old, kudos, baby, you're right. Now, also in your notes, write that the distance across our galaxy is somewhere between 80,000 and 120,000 light years. So go ahead and write that. It's worth noting that a light year is approximately 6 trillion miles in distance. So 1 light year is 6 trillion miles. So if you wanted to know the distance across our galaxy, you would multiply, say, 80,000 by 6 trillion to get that distance. Trust me, it is a long, long way across our galaxy. Now lastly, look at the bottom photo, which shows the thickness of our galaxy. In your notes, write that our galaxy is about 7,000 light years thick. So go ahead and write that down. Now let's take a look at this diagram at where we are located in our galaxy. Now I'd like you to draw a rough picture of our galaxy in your notes. Our galaxy is what's referred to as a spiral galaxy. It has a central hub with several spiral arms coming out of that hub. Now follow along with my lines and reproduce this drawing in your notes. The screen may get a little blurry, but it'll clear up once I'm done drawing. So right here is our central hub. So draw a dot in your notes that represents the central hub of our galaxy. Just kind of fill it in right there. Now we're going to draw several arms that come out. So let's look at the first one. Here's one arm. that comes out, and it's really, I'm pretty new at drawing this arm. So draw that arm on your diagram. Now you're going to want to label it when it first comes out of the central hub as the Perseus arm, which you can see right here. And then out where we're at is called the Orion arm. So in your notes, write that we are located in the Orion arm. Remember, you can pause this, take as much time as you want, and draw as well or not as well, like me, as you want. Now, let's go to the second spiral arm. So follow along. Here's the second spiral arm coming out from our galaxy. So draw that in your notes and label it as the Carina arm, just like the Carina in my third hour, spelled differently. Okay, now let's draw the next one coming out from the central hub called the Sagittarius arm. So draw that arm of the galaxy and label it as the Sagittarius arm. Now let's go to the last one, which comes out this way and spirals out like that. Sorry, I didn't connect those. There we go. Now, the beginning of that arm is called the Centaurus arm, while the outer part of it is called the Cygnus arm. So make sure you have that diagram drawn in your notes. This slide shows a picture of the nearest galaxy to ours. It's called the Andromeda Galaxy. The Andromeda Galaxy is 2.54 million light years away. Yes, 2.54 million light years away. Again, when you look up in the sky and observe this galaxy, and you can, with an average telescope or a good pair of binoculars in the summer, how old is the light that reaches your eyes from the Andromeda Galaxy? Yes, that light is 2.54 million years old. Kind of blows your mind, doesn't it? Now, this is a perfect time to mention the nearest star to our planet. That is, the nearest star other than our sun. We know that our sun's 94 million miles away. The nearest star to us is a double star system called Alpha Centauri. That's ALPHA Centauri, Alpha Centauri. Now, the closest star in that double system is called Proxima Centauri, Proxima Centauri. And that star is 4.5 light years away. Yes, I'm going to ask it. How old is the light from Proxima Centauri once it reaches your eyes? Getting tired of this kind of question? Good, then you're learning. Yes, the light would be 4.5 years old.